Okay, so now let us put things together. So previously we saw last class two algorithms and we analyzed their best case and worst case. And now let us see how can you represent the time complexity using the asymptotic notations we saw. So just a quick review. We saw those two algorithms, sequential key search and finding the maximum integer in the array. For the sequential key search problem, the problem is you're given the array of integers and you want to search for a specific key. Now, if your search key was the first integer itself, we just needed to do one comparison and we can stop the program. On the other hand, if we have to search for the last element in the array, or if the search key is not there, we would have to do n comparisons. Basically, we have to compare with every element in the array and then decide it is in the last index or it is not there. So that's the worst case. We have to do n comparisons. So in this algorithm, we can see the best case, which is one comparison, is definitely different from the worst case, which is n comparisons. Excuse me. One is not same as n. So if the best case is different from worst case, so this is the rule. If best case is different from worst case, we can use only the big O notation to represent the time complexity. We cannot use the theta notation to represent the time complexity of the algorithm. So now what goes inside the big O notation? It is the big O of worst case. So the worst case complexity of the sequential search was n comparisons. And it is right there, where there's no coefficient or there's no lower order term. So we can simply say it is big O of n. So let us say we did analysis like this and it came out to be what we had here, like 4n cubed plus 3n plus 5 is the number of comparisons we do, or the number of times the basic operations in general we do for some algorithm. Then we have to skip the lower order terms and omit the coefficient of the most dominating term and then say this big O of n cubed. Okay, so this is the rule. So if best case is different from worst case, we can use only the big O notation. And what goes into the big O notation is the worst case number of times we do the basic operation. Now for the second algorithm, the maximum integer problem, if you go back to this example, we started with the first element, the element at the index 0 as a temporary maximum and compared that temporary maximum with everything else. If as we go through the array from index 1 to n minus 1, if some other element appears to be greater than the maximum, we update max to be that element value. So we keep on going like that until we compare the last index, and then once you're done with all the comparison, we can say we have found the global maximum, in this case 10. So that means if you look at the logic here, it doesn't really matter where the maximum is. So even if 10 was at index 0 and it is the maximum, we still have to really compare it with every element out there in the array and go through the entire loop from index 1 to n minus 1. So we really have to do all the n minus 1 comparisons irrespective of where that maximum is. So we see then the best case is same as worst case. It doesn't really matter. Given an array of size n, we have to n minus 1 comparisons to find the maximum element in the array. So when the best case is same as worst case, it's like the tight bound scenario. So the most appropriate notation to use is theta. Okay. So we can say the time complexity of the algorithm is theta of n. But since we can say the time complexity is theta of n, theta implies big O, we can also say the time complexity is big O of n. So when I say the most appropriate notation to use, it is theta, because theta gives you a really good picture of the time complexity. Theta of n means that we can say the number of times you do the basic operation is same as a rate at which what goes inside the theta notation, which is n. So that's why I say it's the most appropriate, because if I want to use a big O notation, I can say the time complexity is big O of n square, because the number of comparisons we do is n minus 1, which is n. As n grows to infinity, discarding lower order term n minus 1, we can say it is n. N is big O of n square. By definition of big O, we can say that. or n is equal all to big O of n cube or big O of n to the power 4. That's a loose bound. But that doesn't give us a clear picture of the number of times we do the basic operation for this maximum integer problem. So since the best case is same as worst case, it is more appropriate to use the theta notation to represent the time complexity. So we say it is theta of n. We can say it's big O of n because it is theta of n, theta implies big O. So in an exam when I ask you to write the most appropriate notation, you should use theta. Okay. So why I bring with the big O case here is because sometimes in books, if you see for this algorithm, they would say big O of n, but and that book probably follows a convention of just using the big O notation throughout for all the analysis. But you should remember there are two notations, big O and theta, or big theta, and you should really know when you should use theta and when you should use big O. So the thumb rule is this: if best case is same as worst case, use theta. If best case is different from worst case, use big O and write the worst case complexity, the function inside the big O notation. Okay. Any questions? I have one more example we can go through, but let me come back and see if there are any questions. Okay. Okay, good. So let me go back to this example and just trying to reinforce what we just saw. So this is an algorithm. I have given a pseudo code. Now, given a pseudo code like this, you should be able to figure out what the algorithm is doing. Okay, so you should start getting that skill of finding it out. So let us go through this. So you gain some input, which is n, say an integer, and get inside the algorithm. Now, what it says, if some certain condition, so you know this is an if statement. So if you have a condition, right? So if that condition is true, some condition, you're not even given what condition it is, but if that condition is true, then you get inside the if block and you see a for loop inside the if block. And what we see the for loop does, it runs from I equals 1 to n, so that's like a loop index. And for each index value of I, it doesn't really matter what I index it is, I just want to print some statement. Okay, so that means how many times the statement will be printed? It will be printed n times because the loop is running from index 1 to n. You could print the same statement n times, or you could print the I value along with the statement. That means you can put some message and then say this is index I, 1, 2, 3, 4 and so on. Depends on what you want to print, but basically you're printing something. So each state print operation is, say, takes some time, unit, that's what I say, unit time, some milliseconds or seconds. Now if this condition is not true, then the control does not go inside the if block, it goes inside the else block. So you know from your earlier programming classes, you can have an if else. So in the else block, I have what you call a nested for loop. So here I have for I equals 1 to n, then inside that outer for loop, I have a inner loop that runs from j equals 1 to n. So that means for each value of I, we run this j loop from 1 to n. So and then inside the j loop, you're printing the statement. So that means for each value of I, I'm running the j loop n times, and I'll be printing n times. For a particular value of I, I'll be printing n times. That means now for I equals 1 to n, so the I loop, the outer loop will run n times, and each time I run the outer loop, I am printing n times. So that means totally I will be printing n square times inside the else block. Is that clear? So because this is a j loop, I equals 1 to n, so for each value of I, you run the j loop n times and print each time you run the j loop. So for each index I, you print n times, and the I index goes from 1 to n, so you print n squared times totally. So this is what the algorithm does. So now if you think about what is the basic operation of this algorithm, again by definition a basic operation means the most time consuming operation. And that is done repeatedly if there's a loop. So here we have a loop, and what we do inside the loop is printing. So this printing is the basic operation. So once we decide that is a basic operation, we want to go ahead and find out how many times we do the basic operation. Is there a best case that is different from most case, or every time for a given n input? So that's what we have to decide. So for a given input, how many times we do the basic operation? Is it same irrespective of once we fix the input, it is going to be best case is same as worst case, or it depends on what the input is. Okay, so like the search key problem, remember, so given the in this case are two inputs, an array and a search key. Now how many times we do the comparison depends really on the search key. If the search key is the first element in the array, we just do one comparison. If the search key is the last element in the array, we do n comparison. As in this problem of maximum integer in the array, once you are given an array of size n, you do n minus 1 comparison. So the size of the array is what matters for this algorithm. Here the size of the array is there as n, but the search key is what is deciding how many times we do the basic operation. So it depends on the logic, the algorithm, as well as the input. Like in this case, let us analyze. So once I am given input n, you see it really depends on the condition, which is not known to us what the condition is. So if some condition is true, we print n times. If the condition is false, we print n squared times. That means for a given n, there is a best case which is printing n times, and there is a worst case which is printing n squared times. So for a given input, the best case is different from worst case. Okay, so that means what is the asymptotic notation we can use? That's the final step we have to decide. So the best case is printing n times, the worst case is printing n squared times. So the best case is different from worst case, we have to use a big O notation. We cannot use a theta notation if best case is different from worst case. So use a big O notation, and what goes inside the big O notation, it is n squared, because that's the worst case complexity. Okay. So again, there are no lower order terms or coefficient. You can simply say it is big O of n squared. And we cannot say it is theta of n squared as the time complexity of this algorithm. So think about it. If I say the time complex is theta of n squared, that means you're always printing some function of n squared. That's the number of times you're printing. You're not printing always n squared times. You sometimes may print only n times, and n is not same as n squared. You saw the rate of growth, that's why I presented this table. N is not same as n squared. N grows much slower than n squared. Okay, so that's why for this particular algorithm we cannot use theta notation. Whereas for the maximum integer problem, yes, we can use the theta notation. Always we do n minus 1 comparisons, so it's theta of n. Similarly, in this problem we cannot use theta notation because sometimes we do just one comparison and sometimes we do n comparison. One is not same as n, so we cannot use theta notation. We have to use a big O notation. So for problems like this, we can only get a kind of an estimate of the upper bound. What is the maximum number of times we do the basic operation? Now for algorithms like this, we can get almost exact bound, which is a tight bound. The exact number of times we do the basic operation. Okay. Similarly here, we cannot get a tight bound. We can get only an upper bound. What's the maximum number of times we do the basic operation? Because that's how the logic is programmed here. Okay. So any questions on this? This is very important because we'll use this throughout the course. Yes, so Russell Bishop question. I think everyone can see the messages posted by everyone. Okay, I'll go by each of them. Hanif, what does I equals 1 to n mean? That's like you write a for loop. In a for loop, you write index I equals 1, I less than equal to n, I plus plus, right? So I'm not sure whether you were present last class when I introduced the pseudocode notations. So in this case, when I use a for loop, that's a convention we'll follow. When I say for I equals 1 to n, that's the looping. Okay. Now cell bishop, it means that I'll print n amount of times if condition is 2. Yes, if the condition is 2, you print n times, otherwise you print n squared times. Mark Cole, since we go to second element to find the largest number in the array, the comparison is and the low. Yes. So remember, the array index starts from 0. That's how it does in the C++ and other programming languages. So and also the pseudocode format, we follow the convention. So the indexing starts from 0. So we initialize the temporary maximum, or the largest value temporarily is the first index, which is index 0. And then we go through from index 1 to n minus 1 and see if something else is greater than the temporary maximum. Okay. Good. Okay. All right. So any other question? All right. Let me stop and save.